So this is the outline for the supplementary notes for chapter 32. So first I will let you know what is the differential form of the Maxwell equation. As we have learned in this chapter or in earlier chapter, like we have a Gauss law, we have Ampere's law, and we have Faraday's law. So all these equations is integration form. Actually, for some situation, just like a symmetrical structure, then using the integration form may be useful. But generally, for some situation that is not so symmetric, then the integration form might not be a good choice. So rather than that, we may seek for computer program using some numerical method to solve the E field, B field in the space. In that case, using the differential form will be a better choice. So in that case, in the field of physics, they have both differential form and integration form for Maxwell equation. And as much as we will need to derive the wave equation, we would definitely need the differential form of the Maxwell equation. And so here I will introduce the differential form of Maxwell equations. And then in between, I will let you know the divergence theorem and also the Stokes theorem. And also the conservation of charge. And here I will try to explain why the Ampere's law should also include the displacement current. Because up till now, in chapter 29, you learned the Ampere's law with only mu 0I enclosed on the right side. And here it also tells you that we should also include the displacement current. You may have question of whether we should add the third term, the fourth term, so on and so forth, to make it more accurate. The answer is no, because if we really concern the conservation of charge, up to two terms, the static current and also the displacement current is perfectly fitted. So this is briefly the outline. So first, this is the integral form of the Maxwell equation. As you have learned in chapter 23, we have learned the Gauss law for electricity. So we have this one. We only move the epsilon naught to the right side. So on the right side, we have Q enclosed over epsilon naught. On the left side is the electric flux, or you can actually call it phi E. Okay. And the second one is the Gauss law for magnetism, which is learned in this chapter. So actually, on the left side, it is nothing but the B field. I mean the magnetic flux, the phi B. And as much as we don't have a magnetic monopole, so on the right side we only have 0. Okay, it makes things easier. Okay, so because there is no monopole, no magnetic monopole. Okay, so and the third one is the Faraday's law. This is the line integral of the E field equals the negative of the derivative of the magnetic flux. Okay, so which means that varying B field will generate E field, and here the static current will generate, or the changing E field will generate the B field. So in that sense, changing E field will generate B field, and if the B field generated is also time varying, then it will also generate further E field. Okay, so that's why we will have a EM wave dipole. Okay, so you can clearly see that these two laws are a pair. So on the left side, surface integral of E field, B field, and these two on the left side, line integral of E field and B field. On the right side, some derivative of phi b, derivative of phi e. Of course, this need to multiply by mu naught epsilon naught to make the SI unit matches. And then also here we also include a static current here to make it not so symmetric. Okay, so anyway, this is the integral form for the Maxwell equation. Okay, and here we will try to make things look complicated, but actually this is not so difficult. So just say here on the right side, for the Faraday's on the right side, we have d phi b dt, negative d phi b dt. So in that sense, we can write it as this phi b is actually integration of b dot dA, integration of b dot dA. Of course, this is not a closed surface. This is only bounded by a contour, so we don't have a circle here, but we can actually write it out like this, so that this one look like this one, but not actually the same. This is a surface integral for a closed surface. This is not. This magnetic flux might be varying in time, yes, and it will generate E field. But here we assume a static B field, without any E field changing. Okay, so here we also try to rewrite this phi E to be integration of E dot dA. So nothing special. We just try to write out the definition of phi B and phi E to make it like this and this. Okay, so this is the first step, and then the second step is that in this textbook it only uses a single integral sign for a surface integral, line integral, or even triple integral. But in some other textbook, or especially for calculus textbooks, it will write double integral sign or triple integral sign, because of course in the textbook it only has something like E dot dA, and you know A is area, so it is double integral. But yeah, definitely for a surface integral we can regard it as a kind of a double integral. So some of the textbook it will write a double integral sign. And the other thing we would like to do is we try to write is a Q enclosed to be the triple integral of rho dV. Rho is the charge density. So integrating the charge density over the some region, then it will be the total charge inside the region. So we try to also write this thing as the integration of the triple integral of the charge density. Okay, and then here, as much as it is also a double integral, so we still use a double integral sign. And then here, as it is a line integral, so we only use a single integral sign. And then also here, this I enclosed is like a double integral of J dot dA, which is the definition which we have learned in chapter 26, I suppose. We have learned this definition before. Okay, so we try to convert the original integral form into these 1, 2, 3, 4 equations. Then we can start to move on to another step. And so in short, this is the conclusion. The differential form of the Maxwell equation look like this. You will feel like, oh, what is that? What is this upside down triangle? Okay, so I suppose we have faced this before. In chapter 24, we have learned something like E equals negative gradient V, if you still remember. V is a scalar field, and then taking the gradient will make it become the E field. Of course, you need to take the negative sign. Okay, if you still remember this gradient, this is the gradient operator. Gradient operator in chapter 24 is like partial x, and then I hat, and then plus partial y, j hat, plus partial z, k hat, if you still remember. Okay, so actually, we can really change this 1, 2, 3, 4 integral equation into this partial differential equation. Okay, later I will let you know what is this dot, this cross. Okay, this is actually called divergence. This is the curl. Yeah, later on I will let you know what they are and how we can get those differential form of Maxwell equation. Before doing that, so this is the quick summary. So the integration from the integral form of the Maxwell equation look like this, and the differential form look like this. Okay. You can still see something. As much as you know, this is surface integral. So it changed to divergence. And then this triple integral sign vanish, and then only remain is this rho over epsilon naught. So we have rho over epsilon naught, and then of course this is 0, so this is 0. And then for the line integral, it becomes this upside down triangle, and then with a cross. Okay, so this is curl of E and curl of B. And on the right side, this double integral sign vanish. So we only have partial B, partial T. Okay, partial B, partial T. And then, so the only thing we need to concern is that this original derivative becomes a partial derivative. And then also here, double integral sign vanish. So here we only have mu naught J. And then here we have mu naught, epsilon naught, epsilon naught, partial E, partial T. So you can, even though you don't know what it is, you can see plenty of regulation, plenty of rule inside this conversion from integral form to differential form. Okay, so before we try to let you know how we can get those equations, first I will need to introduce what is divergence and also the curl. Okay, so so as in chapter 24, you already learned gradient operator. Gradient operator is like the derivative in 3 dimensions, something like that. And actually it can, if you still remember, it is E equals negative gradient V. Okay, so you take V and then partial X, partial Y, partial Z, and then this is the 3 component for the E field. And here, actually, the divergence operator is like the gradient dot product with another vector field. So of course here we have at least two types of vector field, like the E field and the B field. B field and E field are vector field. Okay, and of course you can clearly see that this divergence will acting on E field or B field. Also, so as the curl operator will also act on E field and B field. And at least for here, you can safely regard it as the inner operator or the dot product, inner product or dot product, 内积 or dot product. So the one of the easiest characteristic for inner product is like if you have 2 vector, you take the dot product, it becomes a scalar. So here you can regard as this is a vector field, this is a vector field, and then this operator with a dot product become a scalar field. So here this rho is a scalar field. is a scalar field. SCAL, scalar field. Yeah, because the charge density at any certain point is only a number. Whether it is a positive charge density or a negative charge density, it won't have any direction. Okay, so here you can see this is gradient operator, and then if you would like to take divergence to a vector field, so here we just try to write it as f. It can be either E field, B field, or other vector field. So generally, I just write it as f vector field. So for a vector field f, it has an x component, y component, and z component. So yeah, so the solution is like you have this equation. Gradient f is like partial fx, partial x, partial fy, partial y, partial fz, partial z. Reason why is simple. You can just see gradient f is like we try to plug in this one here. So we have partial x, and then I hat, and then plus partial y, j hat, plus partial z, k hat, and then dot product with this f we just place here, fx I hat, and then plus fy j hat, and then plus fz k hat. Okay, pretty much like this. Okay, so here we have a dot product. So it is like a simple product you need to distribute, which is something like in high school you should have learned something like ax squared plus bx plus c times dx squared plus ex plus f, something like this. And then you need to distribute ax squared, multiply this one, and also this one to form 3 terms. And then bx is multiplied to dx squared, and then ex, and then f. So altogether you will have 9 terms, so as this one. So here you can see for partial x, and then I hat dotted with fx I hat, and then fy j hat, and then plus fz k hat, and then plus partial fy j hat dot this one, and then plus partial z, and then k hat dotted with the same thing. Okay, so I don't try to write all the terms because you can clearly find the remaining result. So the first one is I hat dot I hat will be 1. So we only have this partial fx partial x, partial fx partial x. And then the remaining 2 terms will be I dot j will be 0, so it becomes 0. And then also I dot k, I hat dot k hat will also be 0. So we only have this term. And similarly, we have fy j hat here. So j hat dot j hat will be 1. So we will have partial fy partial y. And then likewise, we have fz k hat. So we only have partial fz partial z, partial fz partial z. So that's why it looks like this. And of course, in Cartesian coordinate, it is as simple as this. If it is in other coordinate system, it won't look like this simple. And of course, this is also for Cartesian coordinate. Cartesian coordinate 就是直角六角形。Okay, so only for Cartesian coordinate. If it is like spherical coordinate or cylindrical coordinate, then the expression are a lot so similar. Yeah, if you're interested, you can just check it on Wikipedia. There are very detail even derivation there. Okay, so this is a divergence. Divergence. Okay, so here I try to explain what is the physical meaning of the divergence. So when we try to, actually this physical meaning is something like what we have learned when we learn the Gauss law. At that time we know if we try to calculate the electric flux, and then it is related to the charge enclosed. If this charge enclosed is positive, then there will be something like an E field flux flowing outward. If this Q enclosed is negative, then there will be an electric flux flowing inside the region. Okay, so similarly here, for divergence of F, if we try to consider the divergence of F, if this divergence of F is larger than 0, which means that the field is flowing outward at that point rather than a region, only for that point, and it turns out to be a scalar field. So based on the scalar field, you can see every point whether the field is flowing outward or inward at any point you would like to know. And if divergence of F is negative, then it means that at that point the vector field is flowing inside the point. And if divergence of F is 0, then there will be no net flux flowing in or flowing out at the point. Okay, so this is more or less the divergence operator in Cartesian coordinate. And then next, here we will also learn about the curl operator. Okay, so here we still have this gradient operator, and this is actually the cross product. So when you learn the magnetism, you already use cross product very often. We will need to use the right-hand rule to determine the output vector. Okay, so as you know, for the cross product, we have two vectors having the cross product, and then the result will also be another vector. Okay, so you can also imagine. So this is like the curl of a vector field. Then this whole thing will also be a vector field. And then you can see on the right side, this is a vector field, and then taking the partial derivative with respect to time will still be a vector field. And then also this one, this is the current density. Current density is also a vector field. And then here, E field is a vector field, taking the partial derivative is still a vector field, and then multiply constant will still be a vector field. So these two are vector field, and then this is a scalar field. Okay, so here, still as an example, we just use a vector field F here, and then we try to take gradient cross F or curl of F. So this is a gradient operator in Cartesian coordinate, and then this is also the F in Cartesian coordinate. So we have X, Fy, Fz as the X, Y, Z component. Okay, so for the cross product, we can try to use this determinant 行列式 to really calculate the cross product of these two vector. Okay, so the procedure is like you try to write I hat, J hat, K hat as the first road. And then for the cross product, you should be careful that A cross B and B cross A are not the same. A cross B and B cross A are not the same, it should have a negative sign. So don't try to swap the order of the cross product. For normal product, A times B is B times A, but A vector cross B vector is negative B vector cross A vector. Okay, so here, this is the first vector. Okay, so here we put the x-axis component, y-axis component, z-axis component here, and then we also put the x, y, z component of the second vector in the last row, fx, fy, fz, fx, fy, fz. Okay, so if you don't know how to determine how to calculate the determinant, so for a 3 times 3 determinant, it is easy. Yeah, for 4 times 4 or even larger, then it might be quite tedious. This rule might not be correct, because if this is n times n determinant, it should have n factorial term, n factorial term. So if n is 3 times 3 determinant, it should have a 3 factorial equals 6 term. But if it is a 4 times 4 determinant, it should have a 4 factorial, which is 24 terms. So usually we will not calculate 4 times 4 determinant by hand, except some special case. Yeah, many of the term might be 0, then it might be okay. But generally, only up to 3 times 3 determinant, you may be able to calculate by hand. So the procedure for calculating this is like you try to draw the diagonal line. So I partial y partial fz, and then j, and then go to here, and then also this one, k partial x partial f. And then if it is from top left to bottom right, then we will have a plus sign. We have plus sign. Okay, so let's see. Here we have I hat partial y fc. Let's see, this is I partial y fc. So this is this term. This is the first term here. And then for the second one, j hat partial z fx. Okay, j hat partial z fx. This is the second one. This is the second one. This is the second one. No, this is not this one. It should be this one. This is the second one. And then the third one, k hat partial x fy. K hat partial x fy. So this is the third one. Third one. Okay. So we know how the 3 positive term comes out, and then the next we have the 3 negative term. Okay, so we start from here, I hat and then partial c fy, and then j hat partial x fx, and then k partial y fx, like this. So first I hat, but for these 3 we have a negative sign. We have negative sign. So from top right to bottom left, we have a negative sign. From top left to bottom right, we have plus sign. So here, I had partial c fy, I had partial c fy, we have a negative sign. So this is the 4th term. And then j partial x fc, j partial x fc, j partial x fc. This is the 5th term. This is the 5th term. And then finally, k hat partial y fx, k hat partial y fx. This is the 6th, the last one. Okay. So we have a 6th term for the determinant of a 3 times 3 matrix. Okay, so pretty much it. Okay, so yeah, this is the expression for the curl operator in Cartesian, also in Cartesian coordinate. Cartesian coordinate. Okay, so yeah, so this is the expression, yeah, and then yeah, here is an example for the curl operator. So this is just an example. Don't ask why this is like this. Okay, so this is just an imaginary vector field F in XYZ. Of course, it don't have any Z component and don't have anything related to Z, but yeah, it is still f of XYZ. Okay, so for y is the x component, negative x is the y component, and you can also regard this is plus 0 k hat, something like this. Yeah, adding 0 is 0. Okay, doesn't change. Okay, so here we try to draw it out as shown on the right figure. How to draw it out is not so difficult, although it takes time. So for example, if I just pick a point, let's say the original point, 0, 0, then you just plug in x, y, z to be 0 here, and it is clearly 0. So in the center point, it don't have anything. Okay, let's consider also this thing we know why. And then let's say for this point, this is 4, 0, 4, 0, 0, 4, 0, 0. Okay, 4, 0, 0. So we try to plug in x equals to 4, y equals 0, z equals 0 to here. So this is 0, so it becomes negative 4j. Oh. So this is j direction. This is j direction. This is I hat direction. Yeah. So which means that this is a negative 4j. So we have a long vector pointing downward. Okay. So you just try to plug in all the number into this expression, and then you will be able to draw it out. So a longer vector means the f at that point has a larger magnitude. And then of course it also related to the direction. Just say here, this point is around 440. So if we just plug in x, y, z to be 440, then you will have 4i minus 4j. So you can see this vector is pointing to the bottom right. Okay. So so after we finish the F field, and then you can clearly see that it's like a typhoon. It's like a typhoon. It's something like rotating around this around the z axis. Of course, the z axis is pointing upward. The z axis should be something like should be pointing into the page. Should be pointing into the page. No, should be pointing out of the page, because this is the positive x direction, this is the positive y direction, and then z axis should be like x cross y is the z direction, so z should be pointing out of the page. So yeah, so you can see the F field is like rotating around the z axis. So here we try to plug in this expression into here, or actually we can just plug it into here. Then we can really find that curl of f is negative 2k, because you can see negative 2k. Yeah, you can see here I. So this is fx partial y. So fx partial y is this one. fx is y. So we have a negative y partial y, which is 1. So we have a negative 1, and then here we also have negative x as fy, which means that we have a negative x, and then we take partial x, partial x, partial negative x, partial x, which also gives you negative 1. So we altogether have a negative 2k hat. So here we have negative 2k hat. Other terms are 0. This 1, 2, 3, 4 term, this 1, 2, 3, 4 term are all 0. We only have negative 2k hat here. Okay, so this is negative 2k hat. What does it mean? This is actually the rotational axis, which means that negative 2k is actually something like pointing into the page. negative 2k hat. So it also obey the right hand rule. Okay, your thumb follow this direction, and then your finger will follow the vector field. So yeah, so here, this actually tells you the curl of the vector field is like how the vector field is rotating. Yeah, here you can see this is clockwise and along the x-axis, because if you use your thumb pointing into the page, your other forefinger are clockwise. So yeah, so based on this one, you don't really need to draw it out, and then based on this curl operator, you take the curl of this vector field, it turns out to be negative 2k, then you know the f vector field is rotating along the z-axis. This is k hat is z-axis, and then it is rotating clockwise for the negative sign. Okay, so this is the physical meaning of the curl and also the divergence. Okay, so here we can talk about the divergence theorem and also the Stokes theorem. So first, the divergence theorem is also known as the Gauss theorem. So you can quickly know that this Gauss theorem or divergence theorem is applied for the Gauss law. So it's strongly related to the Gauss law. So yeah, what is the Gauss law? So here is the equation. So on the left side we have the surface integral. Okay, for Gauss law we also have the surface integral for E field or B field. So yeah, we can simply imagine this can be applied for the Gauss law. And on the right side we have a triple integral of this thing. Okay, so you may feel like this is hard to imagine why it would be like this. But at least when you learn calculus, you know something called the fundamental theorem of calculus. Fundamental theorem of calculus. Maybe you don't really care about it. It just tells you integration. The indefinite integral is the enter operator of the derivative. Because when you learn calculus, you know derivative is a definition using the limit. Okay, dy dx should be something like limit delta x tends to 0, and then y of x plus delta x minus y of x over delta x. So this is a definition of the derivative. And then when you learn the integral for the definite integral, it is actually a Riemann sum. So, but when you learn the indefinite integral, you just try to remember what is the antiderivative of a function, and then you try to plug it in, and then plug in the lower and upper bound. So why is this true? So it's based on the fundamental theorem, which means that if you know if f prime of x is small f of x, then when you try to calculate integration of f of x dx from a to b, then it will be f of b minus f of a. So which is like, so we take the derivative. So it's like we take the derivative of this one and then plug in the number. So here it feels like this is a double integral, this is a triple integral. And this triple integral, 3 times of integral, this is 2 times of integral. And then this one of the integral is cancelled with this. Yeah, so here, this is the divergent, and it is still some types of derivative. So it's somehow like this derivative cancel with one of the integration, and then it becomes a double integral. it turns out to be a double integral. So here, this divergence theorem try to link the surface integral with a triple integral. But here we need to take the divergence of this vector field, take the divergence of the vector field, and then take triple integral. Okay, so this is a general case of the fundamental theorem of calculus. Yeah, if you have interest, you can find it on the Wikipedia. Or if you want to know how we can derive it, you can check this link if you are interested in the mathematics or the calculus. Okay, so it says the surface integral of a vector field over the boundary of the volume equals the volume integral of the divergence of the vector field over the volume. So it's interesting. The physical meaning is like you try when you try to calculate the surface integral, which means that you try to this is actually the surface. This is actually the surface. So when you try to calculate the flux, then you try to calculate the divergence for the whole volume. Try to calculate the divergence for the whole volume. And as I mentioned before, the divergence is like for every point inside this region, you try to see whether it is pointing inside or pointing outside. And then, yeah, you can say why we need to calculate the thing inside. But actually for adjacent point, they turns out to be cancel each other. Because for this point, it's falling to the bottom right, this fall to the top left, and then these two will cancel each other. So that the physical meaning is like when you calculate all the divergence within the whole region, only the thing on the boundary remains. It turns out to be the surface integral of this region. Okay, so this is an interesting thing. Yeah, so this is a quick explanation. If you want to know how we can derive it mathematically, you please try to refer to this link to see how we can derive this divergence theorem. If no, then just try to accept this is the divergence theorem. Maybe you will learn it in calculus class. I'm not really sure. When I learn calculus 2, I need to learn this Gauss theorem and also Stokes theorem. Okay, so let's have a 10 minutes break before we